Hi, Integrated Math 1. Welcome to lesson 1.1.1a. Before we get started, though, before we get into today's lesson, we do, of course, have a lovely warm-up to get us started. You also might want to be aware that we are going to do a little bit of cutting and pasting today. So in addition to having your math workbook volume 1, you're also probably going to want scissor and a pencil to write with. You're also going to want scissors and either a glue stick or tape of some kind. That's going to be helpful today. So here's the deal. Emma bought a new video game. The graph shown describes the number of hours spent playing the game over a period of 7 days. All I want you to do with this, I know there's a part 2 on this, but I just want you to do question number 1 today. I just want you to label the axes. That's all I want you to do. I want you to label the x-axis, label the y-axis, given this scenario. Go ahead and hit pause, label your axes, and then hit play to check your work. So period of 7 days, how many video games she bought, and how many hours she spent playing the video game. Well, we know she played for 7 days, and I see points on all 7 of these. So that makes me think that my x-axis is the number of days, right? That leads me to think that my x-axis is time measured in days. Well, if my x-axis is my days, is my time, then that means that my y-axis is the time she spent playing the video game, right? The number of hours she spent playing that video game. So I labeled time playing video game, and I made sure I included hours so that if somebody's looking at this graph, they know what these units are, that our x-axis is the time in days and our y-axis is the time we're playing in hours. So yeah, we're going to start looking at how to understand quantities and their relationships and why all of this stuff is important. And this is day 1 of this lesson. We will, of course, continue on with day 2 later on. But for now, we'll get this party started. So we do have some learning goals over these next 2 days. We want to understand quantities and their relationships with each other. We want to identify the independent and dependent quantities for a scenario. We'll be doing a lot of that. We'll be looking at how to match up a graph with an appropriate scenario. We want to be able to do that as well. And of course, use a reasonable scale for graphing or modeling scenario, right? Like, okay, you know what the x-axis is, you know what the y-axis is, but they need to have numbers on them, right? You need numbers on those axes so you know how much everything is. You want to be able to identify key characteristics of graphs, which we'll play a little bit with more next time, and describe similarities and differences between pairs of graphs and their scenarios. How are they the same? How are they different? We will play with that a little bit more next time. But our key terms for today will be dependent quantity and independent quantity. These are super important key terms that we're going to play with a lot. So you've analyzed graphs of relationships and identified important features, right? You can, in past math classes, you can find this intercepts, x-intercept, y-intercept. You can find slopes. You may have heard of it referred to as rate of change. So here's the thing. How can these key characteristics of a graph tell a story? Because they do. So we have a little getting it started activity. We're on page M1-8. If you're curious where we are in your workbook on page M1-8. And you really got to ask yourself a question when we're talking about independent and dependent quantities. You have to ask yourself, what comes first? Have you ever planned a party? You may have purchased ice, gone grocery shopping, selected music, made food, or even cleaned in preparation. Many times these tasks depend on another task being done first. For instance, you wouldn't make food before grocery shopping, now would you? So you going to want to make sure, hey, what's the first thing that needs to be done? There's an order to these things, right? Again, awkward to make food if you haven't got the groceries to do it. So with that, I have a whole list of things, and I want you to consider the 2 quantities that are changing in each relationship. So with each relationship, how are they changing? And you may even want to start asking yourself, what comes first? What do you need to know first? So the number of movie tickets purchased and the total cost, what would you need to know first? How are they related? The number of eggs used and the number of cakes baked. What do you need to know first? The number of students in attendance at school and the number of lunches served. What would you need to know first? The number of hours driven and the number of miles to a vacation destination. What information would you need first? And the number of minutes a swimming pool is filled with water and the number of gallons of water in the swimming pool. What comes first? So describe how you can determine which quantity is independent and which quantity is dependent in any situation. If something is independent, what does that mean? If something's dependent, what does that mean? And so how would you know which is which? Go ahead and take a stab at this. Just hit pause, make a few notes, and then we'll come back to keep the discussion going. So remember how I kept asking you what comes first, what comes first, what comes first? The independent quantity doesn't depend on anything else. It's going to do what it's going to do, but what you really want to think of is the independent quantity is the one that is necessary to know first. The independent quantity is the thing you want to know first. The dependent quantity depends on your independent quantity. So the independent quantity is the one that is necessary to know first because it affects the dependent quantity. So in your book, you have a little box. There's a lovely little box with some bolded words in them, like they're important or something. So you might want to make a little note there. When one quantity depends on another in a problem situation, it's said to be a dependent quantity. And the quantity it depends upon is the independent quantity. So the independent guy, he's independent, he's going to do whatever he wants to do, but the independent quantity comes first. The dependent quantity then follows, right? The dependent quantity depends on the independent quantity, so it follows that. It's not going to be the first bit of information you want. It's not going to be the first thing you know. So now that we've said that, let's come back to these statements. And sorry, my face is in the way. I'm going to fix that. There we go. Now that we've said that, let's come back to our relationships we were talking about earlier. We said the independent quantity is the one that comes first. The dependent quantity is the one that follows after it. So I would like you, for each scenario, each sentence, I would like you to circle the independent quantity, circle the guy that comes first, and I'd like you to underline the dependent quantity, the one that follows from it. So go ahead and hit pause, make your circles and underlines, and then hit play when you're ready to check your work. So let's start with this, the number of movie tickets purchased and the total cost. Well, first, I need to know how many tickets I'm purchasing. So that's my independent quantity. And that means my dependent quantity is the total cost because the total cost depends on how many tickets I'm buying. The number of eggs used and the number of cakes baked. I don't know about you guys, but I usually like to decide how many cakes I'm baking first, and then I figure out how many eggs to pull out of the fridge. So number of cakes baked, I want to know that first. That's my independent quantity. And thus my dependent quantity is the number of eggs used, right? Number of cakes baked, the number of eggs used depends on how many cakes I'm baking. It's going to tell me how many eggs to pull out of my fridge. Number of students in attendance at school and the number of lunches served. Well, the first thing I need to know is how many kids are at the school. That's my independent quantity, so that I know how many lunches we need to be serving. So there's my dependent quantity, because how many lunches we serve depends on how many kids are in attendance that day, right? The number of hours driven and the number of miles to a vacation destination. Well, how long it takes me to get there kind of depends on how far I am, right? So first I need to know the number of miles to my vacation destination. That's number one. So I circled that for my independent quantity. And then I can figure out the number of hours driven, making it my dependent quantity. Sorry, my lines are getting a little funky there. Number of minutes a swimming pool is filled with water and the number of gallons of water in the swimming pool. Well, I need to know how long that hose has been sitting in the pool first, right? So the number of minutes a swimming pool is filled with water, that's my independent quantity. And then, of course, the number of gallons of water in the swimming pool is my dependent quantity because it depends on how long the hose has been filling up that swimming pool. Maybe I have something bigger than a hose. We just had a hose. It works. So are we getting the idea? The independent quantity is the one that comes first. The dependent quantity is the one that comes after, the one that follows from it, the one that depends on the independent guy. Seems like it's always that way. The dependent ones always relying on us independent ones. It's all good. All right. Let's keep going then to page M1-9, and let's see if we can start connecting scenarios and the graphs and figuring out how everything goes together. There we go. While a person can describe the monthly cost to operate a business or talk about a marathon pace a runner ran to break a world record, graphs on a coordinate plane enable people to see the data. Graphs relay information about data in a visual way, right? We can see what's going on. It makes a difference. Now, when we do these graphs, you can use lines or smooth curves to represent relationships between points on a graph. In some problem situations, all the points on the line will make sense. In other problem situations, not all of the points will make sense. So when you model a relationship with a line or a curve, it is up to you to consider the situation and interpret the meaning of the data values shown. So this is where you want to bust out your scissors and either tape or a glue stick, something like that. That's where we're busting these out. So this activity includes 8 scenarios, and you have all the scenarios. You see them in these coming pages on your graph starting in M1-9. But it also includes 8 graphs that are located at the end of the lesson. So if you flip over in your book to page M1-17, you will see these graphs. So here's what you're going to do. First, cut out all your graphs. If you need to hit pause right now and cut out, I can say it, cut out all your graphs, go for it. Just be careful. Make sure you don't cut off A, B, C, D, E, F, G. It'll make it a little easier. So go ahead and right now hit pause, cut out all your graphs, and then come back to me. All right, you've cut out all your graphs. You've got them sitting there, ready to go. Here's what you're going to do. Here's what you're going to do. And there's a lot of steps here, so make sure you follow them all. So first, obviously, read each scenario. Read the scenario, right? What's going on, what's happening, all that good stuff. Then, once you've read the scenario, just like we did before, right, in our getting started activity, determine the independent and dependent quantities. That's the next step. Once you've done that, and you'll see there's space to write independent quantity, dependent quantity, you can write them right underneath the scenarios. Then match each scenario to its corresponding graph. So figure out which of your 8 graphs matches that scenario. And you're going to attach that graph next to the scenario. You can glue it in, you can tape it in. Don't use staples because they leave bumps and it makes it hard to take your notes later on when you flip the page. So use glue stick, use tape, something like that to match up your graphs to each scenario. Then, there's more, one last thing. For each graph, I would like you to label the X and Y axes with the appropriate quantity and a reasonable scale, and then interpret the meaning of the origin. So at this point, label your x-axis, label your y-axis, make sure you give me the units, right? That's what it says by appropriate quantity. Is it hours? Is it minutes? Is it miles? I don't know. Tell me. Just like we did at the very, very beginning in our warm-up. And make sure when it says reasonable scale, that means number your x-axis, number your y-axis. Make sure you're using numbers that make sense. Yeah. And if you've got time, I get it. If you don't have run out of time, it's cool. If you have time, interpret the meaning of the origin. If you don't have time, I won't judge you for that. It's all right. There's a lot happening here. So it starts on page M1-9, 8 scenarios. Dive in and go. Hit pause, work all these out. Make sure you do all of it. In fact, I'll put my directions back here. For each one, read it, determine the independent, dependent quantities, write it down, match the graph, label the graph. You got this? All right. Hit pause to go through all 8 scenarios and work this out, and then hit play when you're ready to check your work, see how you did. All right, scenario number 1, Daredevil. Grayson completes a dive from a cliff 75 feet above a river. It takes him only 1.5 seconds to hit the water, and then another half a second to descend 10 feet into the river. So I thought, all right. The independent quantity here is time. In this case, time in seconds. And that's because time is always independent, guys. Time is almost always independent, right? Time depends on nobody. He's going to do what he's going to do. The dependent quantity then, is going to be Grayson's height above the water in feet. The reason for this is because how high off the ground Grayson is depends on how long it's been since he jumped off the cliff, right? That's just kind of how this works. The graph that went with it, the graph he should have chosen was graph E. In fact, it looks like he's jumping off a cliff, right? It looks like he's up here and he's like, jump! And then he hits the water and slows down a little bit once he gets in the water. So let's label it. We said time was the independent one, so I'm going to label my x-axis as time in seconds. And like I said, it looks like this is him jumping off a cliff. So I'm going to say that my y-axis is Grayson's height above the water measured in feet. It did mention the origin. I said you didn't have to worry about that. But if you did want to mention the origin is actually at the water level, isn't it? And it's also at 0. So if we're talking about the height, it's the water level. If we're talking about time, it's a 0 seconds. So the origin would be if you were at water level when Grayson jumped off, which he wasn't, but he could have been. I did go ahead and put numbers on here. It said it took him 1.5 seconds to hit the water, and then only a half second once he was underneath the water, and he went 10 feet down. So 10 feet down, and then I counted up from here. This is terrible. That should be moved up. That should be moved up. You think I can fix it? I think I can fix it. Hang on. Oh, check my Scott's knobby stalls. I'm going to fix it. Maybe I'm going to fix it. I'm going to take this bad boy and I'm going to scoot it up. Maybe. Oh. There we go. Oopsie, just kidding. There you go. So that would be 10 feet, 20 feet, 30 feet, 40 feet, 50 feet, all that good stuff, because that would put him at 75 feet when he jumped off the cliff. Sorry about that. That was a little off, but it was an easy fix. Skills, I have them. All right, next scenario. Candace is a building manager for the Crowley Enterprise office building. I like that this is called something fishy. One of her responsibilities is cleaning the office building's 200-gallon aquarium. That's so big. For cleaning, she must remove the fish from the aquarium and drain the water. The water drains at a constant rate of 10 gallons per minute. All right, independent and dependent. Well, I don't know about you guys, but if you recall from the earlier scenario, we said time tends to be the independent one. So time is our independent quantity, the time in minutes. That's what we would need to know first, right? How long it was draining before I could tell you how much water had drained out of it, making that our dependent quantity, the water in gallons. There you go. The graph that went with this, graph H. So we start high and then it's just constantly draining. And there you go. Ooh, that means I need to label my x-axis and y-axis. So I'm going to label my x-axis as time in minutes. I'm going to label my y-axis as water in gallons. I should number my axes, label everything. So I just counted, 1 minute, 2 minute, 3 minute, 4 minutes. It did say that it was a 200-gallon aquarium. So if this bit up the top is 200 gallons, then that means we must be counting by 20s, 20, 40, 60, 80, 100, 20, 40, 60, 80, that would be 200. Next, smartphone. But is it a smart deal? I don't know. You have your eye on an upgraded smartphone. However, you currently do not have the money to purchase it. Your cousin will provide the funding as long as you pay him back with interest. I'd be questionable about that cousin. He tells you that you only need to pay $1 in interest initially, and then the interest will double each week after that. Consider his offer and wonder if this was really a good deal. So, my independent quantity, you know what it is. You know what it is. It happened the last two problems. It's going to happen again. The independent quantity is time, right? I need to know how long it's going to take me to pay him back. That's the first thing I need to know. And so time measured in weeks in this case, right? He says $1 and then it's going to double each week. So my time is measured in weeks. And the dependent quantity is the interest in dollars, right? How much interest I'm going to pay depends on how long it's going to take me to pay him back. It's going to depend on how many weeks it takes to pay him back. The graph that goes with this one is graph B, because there's a thing about doubling, right? It's not increasing at a constant rate. Like you pay $1 and then you pay $2 and then you pay $4 and then you pay $8 and then you pay $16 the following week. This is getting crazy. So it was this nice upward curve. It's getting expensive fast, people. X-axis then is our time in weeks. Our y-axis is our interest in dollars. Don't forget to number your axes. So 1 week, 2 weeks, 3 weeks, 4 weeks. Look at this. After 5 weeks, how much money you already paying your cousin in interest? And that's on top of the money you got to pay him back for. This cousin is sketchy, man. And so it looks like we have $10, $20, $30. Look at this. By the 5th week, you have to pay your cousin $32 in interest on top of what you already got to pay. It's not right, man. It's not right. Can't wait to hit the slopes. Andrew loves skiing. He just hates a ski lift. That's fair. I don't like heights either. To make matters worse, the ski lift has been acting up today. Andrew is using the GPS on his phone to track the ski lift's progress as it travels up the mountain. It moves at a steady rate of 400 feet per minute until it stops suddenly. Andrew calls his friend to tell him that he is stuck. They talk on the phone for 10 minutes, right? Your phone tells you how long you've been talking, until finally the ski lift begins moving again. I know you know what the independent quantity is. I know you know what the independent quantity is. It's the time in minutes. You seeing a pattern here? Maybe. Independent quantity is time in minutes, right? That time is moving forward whether or not that dumb ski lift is working. So what's the dependent quantity? Well, we're moving at a rate of 400 feet per minute. It sounds to me like my dependent quantity is my distance in feet. Yep. This darn thing. So what's the graph that matches it? Well, it's graph G. We were moving up the mountain and then we weren't until we started moving up the mountain again. So graph G is a perfect little guy for this scenario. And of course, my x-axis is my time in minutes. My y-axis is my distance in feet. And since my x-axis is in minutes, we're just going to count off the minutes. I am counting by twos, 2, 4, 6, 8, 10. Because if you recall that flat bit where we were moving, that's 10 minutes, right? So 2, 4, 6, 8, 10. That's 10 minutes right there. My y-axis is our distance, and it says 400 feet per minute. So we're going to go 400, 800, and work our way up from there. Darn ski lift. It's magic. The amazing Aloysius is practicing one of his tricks. As part of this trick, he cuts a rope into many pieces and then magically puts the pieces of the rope back together. He begins the trick with a 20-foot rope and then cuts it in half. He then takes one of the halves and cuts that piece in half. He repeats this process until he is left with a piece so small he can no longer cut it. And hang on, I've got some, it went a little funky there, didn't it? I'm going to fix it. Do you want to see? I'm going to fix it. I'm going to fix it. Better. 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 Oh, that looks way better. See, look, already I made it better. Magic. I've got skills. All right, so the independent quantity. Now this one's different. There's no time, right? We've been kind of defaulting to time on this. This one's a little different. The independent quantity in this case is the number of cuts he makes, right? And the dependent quantity is the length of each piece of rope measured in feet. And here's why. In order for me to know how long the rope is, I first need to know how many cuts. Right? If I know how many cuts he made, I can be like, okay, cut it in half, cut it in half, cut it in half, cut it in half. If I know how many cuts he made, I can figure out the length of each piece of rope. If I don't know that, I can't figure that out. So first I need to know the number of cuts he made, and then I can figure out how long each piece of rope is. So in this case, the rope was getting smaller and smaller and smaller and smaller. So the graph I picked for this one was graph D, because we kept cutting in half, right? We went from 20 feet down to 10 feet, down to 5 feet, down to 2.5 feet, right? Just boom, boom, boom. So my x-axis is my number of cuts, and my y-axis is the length of each piece of rope measured in feet. And I went ahead and just numbered the cuts, 1, 2, 3, 4, 5. And we said we started at 20 and then came down. So it looks like we are once again counting by twos, 2, 4, 6, 8, 10, all that good stuff. Baton twirling. Jill is a drum major for the Altadena High School Marching Band. For the finale of the halftime performance, Jill tosses her baton in the air so that it reaches a maximum height of 22 feet. This gives her 2 seconds to twirl around twice and catch the baton when it comes back down. You're not going to be surprised by this one. Our independent quantity is time, measured in seconds, right? She's got 2 seconds to do her twirl. The dependent quantity is the height of the baton measured in feet, because how high the baton is depends on how long it's been since she chucked it in the air. And I bet you totally figured out which graph this was, right? She threw it up and then it came right back down. So I picked graph F. Yay. And notice it doesn't hit the ground, right? She's catching it. She has it in her hand and she throws it and then she catches it. So theoretically, that baton is not going to hit the ground. It's not going to reach zero. We hope. So my x-axis is the time measured in seconds. My y-axis is the height of the baton measured in feet. And we need to label this thing. We said it gives her 2 seconds from when she throws it to when she catches it. So from here to here is going to be 2 seconds. So I cut that into quarter seconds, like a quarter, a half, 3/4, 1, 1 1/4, 1 1/2, right? They've only got 2 seconds to do your twirls. It did say it reached a maximum height of 22 feet. So this should be 22. So that makes me feel like this number is 20. So I went ahead and counted by threes of all the weird things. 3, 6, 9, 12, 15. I know that seems weird, but it fit the graph. It fit. All right. Cold weather. I don't do cold weather. Why do you think I live where I live, man? The number of guests at a ski resort on any given day is related to the day's high temperature. If the high temperature is negative 20 degrees Fahrenheit or below, no one comes to the resort. Nobody wants to go skiing and die. As the temperature increases, so does the number of guests. Once the temperature reaches 0 degrees Fahrenheit and increases through the single digits, the number of guests soars. If the temperature is 10 degrees Fahrenheit or higher, the ski resort is at full capacity with 400 guests. So this one's a little different. There's no time on this one, right? You got to think this through a little bit. The independent quantity is the temperature in degrees Fahrenheit. I don't control the temperature, all right? The weather is going to do what the weather is going to do. The dependent quantity is the number of guests, because we've noticed the number of guests we have depends on the temperature. If it's too cold, nobody's coming. As it warms up, more people come. And then, of course, from 0 to 10 degrees, it just gets crazy. Like everybody and their brother is freaking showing up for this mass. But at some point we top out. The resort can only hold 400 guests, and so at some resort we will top out. So as a result, I picked graph A, right? We're increasing, and then there comes a point where it's just like, and we're really increasing, and then it tops out and we can't fit any more people in. Notice my y-axis is in the middle this time. Did you catch that? That one's a little weird, but there's a reason. Because my x-axis is the temperature in degrees Fahrenheit and my y-axis is the number of guests. So the reason it looks like this is because, remember, our temperature started at negative 20 degrees Fahrenheit. And that means that my little guy's again crooked. Hang on, I'm going to fix that. I'm going to fix that. I'm going to fix it. All better. So 5, 10, 15, 20, because this is negative 20 all the way back out here. And of course, this was the number of guests. We start with 0 guests and we work our way up to 400 guests. So it looks like we're counting by 50s on our y-axis. Yay. Last scenario, we're almost there. The jelly bean challenge. Oh, yeah. Oh, I got to get back to where I can see what I'm doing. There we go. Mr. Wright judges the annual Jelly Bean Challenge at the summer fair. Every year, he encourages the citizens in his town to guess the number of jelly beans in a jar. He records all the possible guesses and the number of jelly beans that each guess was off by. So not how many jelly beans they guessed. He judges it by how much they were off. Fair enough. So the independent quantity, oddly enough, is the number of jelly beans guessed, right? People making all kinds of guesses. And Mr. Wright has no control over that. It's pretty independent for each person. The dependent quantity is the number of jelly beans the guess is off by, because how much they're going to be off depends on what these people guessed in the first place. And you've probably already figured out there's only one graph left. Graph C is the only one left. Now it has this V shape. Why? Because clearly this is the number of jelly beans in the jar, isn't it? But people who guess too big are off by this much, and people who guess too small get more and more off as they go to the left. So that's why this graph looks the way it does. So our x-axis is a possible number of jelly beans, all the guesses everybody makes. And our y-axis is the number of jelly beans the guess is off by. So for my, I don't know, this one was wide open. You actually could have put any numbers here you wanted to, because I have no idea how many jelly beans Mr. Wright put in that jar. We're going to say he put 500 jelly beans in the jar and counted by hundreds. And I honestly don't know. And then we'll say how much people are off by. We'll count by hundreds as well. I really couldn't say. Mr. Wright gave us like no numbers here at all to work with. Fair enough. All right, guys, as always, I hope you found this helpful. I hope you found this useful. If you have questions or concerns, email me, come see me during office hours, come talk to me, and I'll see you guys soon. Bye.